So let me know if you can see the screen.
Yes.
Okay, so just a second. Let me shift it. This side. Maybe not. Okay, so last time we saw how to design some combinational circuits. I think before that we saw how to design basic gates using Verilog. Last time we saw how to design an adder using Verilog. Now this was one of the examples where we saw a single bit adder and that was instantiated 4 times to create a 4-bit adder. So this was a structural way of doing design. Then we saw the same adder, 4-bit full adder, can be designed using a behavioral description in Verilog. There is one more way of doing design is, now let's say again we are also implementing a full adder again. In this case, it's implemented using basic gates, NAND gate, XOR gate, etc. So how do we do that? First, we have two separate modules for NAND 2 and XOR 2, two input gates. Module XOR 2 Y, comma A, comma B. This is my port list. Y is a single bit output port. A and B are single bit input port. Assign Y is equal to A cap B. So this cap sign is for XOR. Assign Y is equal to A XOR B on a continuous basis. This is a continuous assignment. So on a continuous basis, Y will get A XOR with B, end module. So this is a two input XOR gate. Now if you look at the two input NAND gate, module NAND 2 Y comma A comma B, output Y single bit, input A and B single bit inputs. Assign Y is equal to NOT. The sine wave is a NOT inversion. A and B. So A and B then inverted will give me a NAND gate, end module. So this is the NAND gate that I would need here 1, 2, 3 times, and this is the XOR gate I'm going to need 2 times. So I go to my full adder module full add. CO carry out, sum is S is sum, A, B, C are input, C is carry in, out of which CO and S are single bit output ports. A, B, and C are single bit input ports. Now I need a wire called N1, N2, and N3. I need 3 wires. Why do I need them? If you see in the circuit below here, N1 wire is connecting the output of the first XOR gate to the input of the second XOR gate. N2 wire is connecting the output of the NAND gate to the input of the third NAND gate here. And N3 wire is connecting the output of second NAND gate to input of third NAND gate. So I need these wires. So wire N1, N2, N3, each of them is a single bit wire. Now I'm going to instantiate my components as required. XOR gate will be instantiated 2 times. NAND gate will be instantiated 3 times. Instantiated means I'm going to create a copy of gates and I'm going to create the port mapping. So XOR 2, then the label for this instance XOR underscore 1, then the port mapping. Dot Y, dot A, and dot B are name of the XOR 2 ports, module XOR 2 ports here, if you see on the right hand side top here. So dot Y goes to N1 local wire here. Dot A goes to local A port here. Dot B goes to local B port here. We're talking about this XOR gate in the bottom circuit that you see here. This is the first instance of the XOR gate. XOR gate number 2 instance, XOR 2, XOR underscore 2. This is the label for this instance. Again, I'm going to do port mapping. Dot Y goes to S, which is the output as output of this XOR gate. Second goes to output S. A dot A second input goes to N1. N1 is connected to the second input of to the first input of second XOR gate, and C is connected, which is the third input, is connected to the second input of this XOR gate. So this B goes to C, as you see here. So XOR 2 instances have been done. So 9 2 I'm going to instantiate 3 times. 9 2 9 underscore 1 is the first instance labeled dot Y goes to N2, dot A goes to A, dot B goes to B. Dot Y, dot A, and dot B are again port names of this NAND 2 module that you see on the right hand side here. And bracket N2, bracket A, and bracket B are local signals or local wires at the current module, full add in this case. It could be input output ports or it could be local wires in that. Dot y, dot a, and dot b are called formals. Anything in the bracket are called actuals. So formal is mapped to actual signal. So this is the first and NAND2 instance. Now I'm going to instantiate the NAND2 gate again second time. Call it NAND underscore 2 label. Dot y goes to N3 here. Dot A is connected to N1 here. Dot B is connected to the C input here. Dot B is input connected to the C input here. So this is the second NAND gate. Third NAND gate, NAND2 instance label is NAND underscore 3. Dot Y goes to CO, which is a carry out here. Dot A goes to N3. N3 is the output of the second NAND gate connected to the third NAND gate input. Dot B is connected to N2. Then, so this structure is done, so end module. So what we have done here is we have created a full adder using basic gates. Each basic gate will have a separate module, and then in the full adder module I'm going to instantiate these basic gates as required. XOR gate, 2 input XOR gate will be instantiated 2 times. NAND 2 gate will be instantiated 3 times. End module. So this is called a structural way of doing design. Why? Because I'm creating a structure of this full adder design myself. In this case, using basic gates. Any questions?
No.
So please note down this design. I'm going to ask you later on. Once we finish designs, I'm going to ask you to create test benches for the existing designs that we have seen. And plus, I will give you a couple, at least a few more designs to practice. So since you have this design ready for this particular design, you will only have to write a test bench and then simulate the design. So please note down this design. I will also quickly go back one more slide and have you note down the same full adder but with other methods. You can choose any method you want.
I think I'm ready.
Done? Okay. Next slide.
Yeah,
Sorry, you want to wait?
no, I'm done.
Done? Okay. Next slide. Okay, done.
Yeah.
Okay, next slide. Okay, so done. Let's wait till Nitin is done, then we'll go forward.
Yeah, done.
Okay, so one thing I would like to mention here is please remember that Verilog is a case sensitive language. So anything mentioned in capital, in this case, Y, A, and B are in capital, the port names. So it has to be in capital in this case where you are instantiating and doing the port mapping. You cannot have lowercase here, uppercase here, or lowercase here, uppercase here. That will not work. Whatever case you're using has to be consistent throughout the modules since Verilog is case sensitive. Okay, so modeling structures. Now, modeling structures or a model or Verilog, as you might remember, we saw the history of Verilog. It started out as a modeling language, and then synthesis was invented, and we could convert a model, a Verilog model, to hardware. So, modeling is a word used quite frequently. It means design also, but that's a wording used quite frequently. That can be done using various syntax or various statements in Verilog. One is a netlist. You can create a structural description of the design like we just saw. Then we can use continuous assignments like we saw again using continuous assign statements here. So that is typically called data flow modeling also. So data flow modeling strictly is done using continuous assignments at a parallel level. Or we can have procedural blocks. Procedural blocks, as we have seen, are of two kinds: always blocks and initial blocks. Inside the always block or inside the initial block, we will be using behavioral description of Verilog, where it can allow us timing control, concurrency, and we'll see how that concurrency comes into picture, which are basically like C-like statements. So anything inside the always block or anything inside the initial block is sequential execution. In this case, this always block, inside it is there are two statements. First, this statement will be executed for some, then cout statement will be executed. Anything inside the always block is sequential. Now in this case, this design, we only had one always block. Imagine that we have three always blocks for some design: always block 1, always block 2, and always block 3. The logic of always block 1 will work parallelly or concurrently with respect to logic of always block 2, and that will work parallelly with respect to always block 3. That is how you can build concurrency in Verilog. If you want to execute parallel logic, put that logic in two separate always block. That will work parallel. But anything inside the always block is sequential, one after another, just like C language. That's what this talks about. Then we can have primitives also. Not that anybody uses them anymore, but we have primitives are basic gates: AND gate, OR gate, NAND gate, etc. So if you want, you can use them. We can also include functions and tasks in Verilog. Functions and tasks are both kinds. They are a type of subroutine in Verilog, which we'll see later on when we see function and task section. That can also be included for modeling purpose. As we just saw, there were primitives are used in Verilog, but now anybody, not a designer, doesn't use them anymore. So it could be used by the synthesis tool if it is required. Basic primitives are basic gates like AND gate, OR gate, NOT gate, any buffers, etc. And the basic gates can be 2 input, 3 input, 4 input depending on the requirement. Or the synthesis tool might create a 3 input NAND gate using 2 input NAND gate, like what we saw earlier for a AND gate design. We had created a 3 input AND gate design using 2 input AND gates. So that can also be created internally. Verilog supports operators. There are various kinds of operators supported by Verilog language. What are the arithmetic operators? So plus, minus, star, slash, percentage. This is addition, subtraction, multiplication, division, giving you quotient, and percentage is division, giving you remainder. Both are division operation. First, this slash forward slash will give you quotient of the for the result. Percentage is a division operator which will give you remainder as well. Then we have relational operators: less than, equal to, greater than, equal to. These are used for comparison purpose. You can compare if two numbers are less than, equal to, greater than, equal to with respect to each other. Same goes with equality operators. Now there is a slight difference where 2 equal to and 3 equal to's are used. We'll see in I think the next slide or after that. So equal to means you're checking if two numbers are equal. Exclamation mark equal to means you're checking if two numbers are not equal. Same thing goes with 3 equal to or this not equal to. We'll see what that means shortly. We have logical operators. Logical operator, this is inversion operator, this is and, this is or, logical or. Then we have something called bitwise operators. This is inversion, ANDing, ORing, XOR, XNOR. Then we have something called unary reduction operator. We will also see what that means shortly in one of the examples. Shifting, so we can shift the values right or we can shift the values left as required. We have conditional operators. Now this conditional operator will be used quite a lot, and we have a lot of examples later on this. The conditional operators are denoted by this question mark and colon sign. And we can concatenate numbers. Let's say we have two 4-bit numbers. If we concatenate them, it will create an 8-bit number for us. For that, we have to use this curly brackets to concatenate the numbers. So these are the operators supported by Verilog language. It's the same slide in this different format. So let's take an example how this works. Let's say we have two numbers A and B. Each is 4-bit. A is 1011 value, B is 001 or 0010. Now if I do a logical operation A or to or B, this is a logical operation giving me Boolean result. If this is non-zero, it will give me 1. A and B, if one of the inputs is 0, it will give me a 0 output. This is a Boolean result, so it will either be 0 or 1. So the result of and operator is 1 if none of the operand is 0. What are the operands A and B? If they are both are non-zero, means the output will be 1 and logical operation. The result of the or logical or operation is 1 if at least one of the operands is non-zero. One of the operands is non-zero, logically ORing will give me 1. So it is basically checking if one of the bits is 1. In this case, it's a 4-bit number. One of the operands is non-zero means at least one of the bits will be 1. In that case, the Boolean result will be 1. If one of the operands is 0 and we are doing logical ANDing, that means all 4 bits will be 0. That will result in a 0 Boolean output. True, false or 0, 1. That's a Boolean output. Let's take how a bitwise work. Now A bitwise ORing with B. You see here it's a single OR sign. Two OR sign means logically ORing. Single OR sign means bitwise ORing. We are going to do a bitwise ORing between A and B inputs. What is A? 1011. What is B? 0010. So this is bitwise means LSB, which is 1, bitwise ORed with LSB of B. 1 OR with 0 is 1. Then the next bit, 1 OR with 1 is 1. 0 OR with 0 is 0. 1, the MSB bit, 1 OR with 0 is 1. The result will be 101. A bitwise ORing with B. A bitwise ANDing with B will give me Take LSB again, 1 AND with 0 is 0, 1 AND with 1 is 1, 0 with 0 is 0, and 1 AND with 0 is 0. So 0, 0, 1, 0 will be the result of A bitwise ANDing with B. Then you have something called unary reduction operator. How is that denoted? Now this is a unary reduction OR operator, single OR sign, and with A. So A, all the bits are logically bitwise OR with the same A value, bit by bit. Now A is 1011, and we are doing unary reduction OR operator. Means we take it from the MSB side. MSB 1 will be logically OR with 0. 1 OR with 0 is 1. 1 OR with 1 is 1, next bit. Then 1 OR with 1 is 1. We go all the way till finally a 1 bit result is remaining, which is 1 in this case. Now if I do a unary reduction AND operator with A, which is the operation with itself, 1 AND with 0, this MSB bit AND with 0 is 0. 0 AND with anything is 0. 0 AND with anything is 0. Result will be 0. Unary reduction operator is the logical operation between the bits of the same signal till you get a 1 bit result. Fine. Then we have something called case equality, X case equality and case inequality operators, which has this 3 equal to sign and not equal to sign. So what we saw earlier here, equality operators will check if A is equal to B, and this will check if A is not equal to B. Now this 3 signs is checking if A is equal to B in case A or B has X or Z in it. If you remember Verilog, there are 4 values that are allowed technically: 0, 1, X, and Z. 0 is logic 0, 1 is logic 1, X is unknown state, and Z is a tri-state or a high impedance state. If your A is, let's say, 1X11, and let's say B is 0Z10, then you will have to use 3 equal to if you want to check if A is equal to B. This is checking if A is not equal to B. If one of the operands, any one has X or Z in it, then you have to use this for equality comparison. Now this X and Z being in one of the operands is not supported for synthesis purpose. Synthesis purpose, both signals have to be properly resolved to 1 or 0. So it should be in 1-0 format, binary format. But for simulation purpose, if you want to check two numbers which could have X or Z in them, you have to use this 3 equal to or this for equality comparison. Any questions on this slide?
No.
No? Okay. So feel free to note down small points in your notes so you remember it later on. You can always refer to those notes later on. You don't have to read a book every time. Conditional operator. How does a conditional operator work? Now let's say we want to build a mux. Let's take this example first on the right hand side. Now we have a 4:1 mux where 4:1 mux means 4 inputs, 1 output, 2 select lines. To select n number of select lines, 2 raised to n number of inputs, 1 output. That's how mux work. 2 select line means 4 input and 1 output. If select line is 0, IA value will go to Z output. If it is 0, 1 select line, IB input will go to output Z. If select line is 1, 0 input C, IC input will go to Z. Select lines are 1, 1, then input D will go to output Z. To declare this in Verilog, we use conditional operators. Assign. Now this is using a continuous assign statement outside the always block. Assign Z is equal to concatenate S1 comma S0. So S1 and S0 are single bits. If you concatenate them, you get a 2-bit binary number. This after concatenation you check equal to 2 tick B00 question mark IA. That means check if S1 S0 is 00, 2-bit binary number 00. If it is 00, input A goes to output Z. Else S1 S0 is equal to 2 tick B01 question mark IB. If this is not true, check if this condition is true. If S1 S0 is 2-bit binary 01. If this is true, input B goes to output Z. Else, check for this condition. S1 S0 is 1 0. Input C goes to Z output. Else S1 S0 should, if it is 1 1, input D goes to Z output. And there should always be in the conditional operator a default value. Now, since it's a 2-bit number, it can only change between 0 0 to 1 1, but we should always have a default value, else 0 is assigned to output C. That's how the conditional operator works. Now, if you take um, yeah, so now this conditional operator, it can be, this logic is declared using a continuous assign statement in a data flow modeling method. Data flow can be clubbed with behavioral modeling. Sometimes it is clubbed with structural, sometimes it is clubbed with behavioral. Ultimately, you will have mixture of everything. If you take purely behavioral modeling, the same logic can be described using purely behavioral modeling like this. Ret Z. Why ret Z? Because I'm going to assign Z inside the always block. So a reg has to be declared. Always at S1 or S0. These are my inputs. Only when the select line changes, the input will get appropriate input will go to output. Always at S1 or S0. This is my sensitivity list. Begin the always block if S1 S0 changes. Begin as Z is equal to this. So the same logic, instead of continuous assign statement, I'm going to say Z is equal to this. End the always block. So this on the right hand side that you see here is a behavioral modeling style. This is a data flow modeling style. Any modeling style can be used as per your convenience. Both are okay. Here, as you see here, we are not looking at module, input, output ports, everything. We assume that you know how that is declared. We are looking at only the core logic for this purpose, mux purpose. And on the bottom, there is another example. This is a 2:1 mux. If op, which is stands for opcode, is equal to add, check if opcode is add, then the adder output, which is here, goes, which is coming as an input to the multiplexer, adder output, that is going to output S. If opcode is not equal to add, then the subtractor output, which is coming as the second input to the multiplexer, goes to output S. So if you look at the code for this, what the Verilog code looks like, assign S is equal to op equal to add question mark A plus B. If op is equal to add, A plus B goes to output S. If op is not equal to add, A minus B goes to output S. A plus B is the adder output, A minus B is the subtractor output. This is the Verilog code for the small block here. Any questions on this? How conditional operator works?
No.
Okay, so if you want, I can just add a, so it will be easier for you.
I have a screenshot.
Yeah, I'm just going to add a input output port to it so you can note down this as a design.
Okay.
So I might have to. Okay, fine.
So a quick question.
Yes.
At the end of all this, there's this one BO. What's is it the output? Just before the end of the module, just the line above.
This one?
That one, yes.
This is a
Yeah.
default value. In case S1, S0 doesn't match any of these combinations, 0, 0, 0, 1, 1, 0,
Oh,
1, 1. By default, 0 will get assigned to output Z.
okay.
So this is how the this thing will look like if you look at a module perspective. So you can, if you want, you can note down this, and which can be a 4 input multiplexer for you.
Yeah, I'm done.
Okay. So numbers we have seen that numbers can be represented in different formats. It can be decimal, it can be binary, it can be hexadecimal. We don't really work with octal numbers anymore, so we'll ignore them for now. Decimal numbers have a base of 10, binary numbers have a base of 2, and hexadecimal numbers have a base of 16. So 16 decimal, now if I just to refresh your memory, 16 decimal will be binary how much? What will be the equivalent binary for 16 in decimal?
1111, 4 ones.
4 ones.
No,
Will that be
in decimal.
yeah.
No, it's one.
Hello?
1 and 4 zeros.
1 1 and 4 zeros, is that it?
No, just 1 1. Yeah, and 4 zeros.
1 1 and 4 zeros. Okay, any other answer?
I 1 and 4 zeros. Yeah, I think that's it. 1 and 4 zeros. Yeah.
Okay. So if it's a 8-bit number, it will be 00010000. Now why is that? Decimal 16 is binary. 8 tick B means 8-bit binary number. 8 tick D16 means ultimately it will use 8-bit binary number inside it, but it's a decimal 16 value. 2 raised to 0, since it's a binary number base of 2, 2 raised to 0, 2 raised to 1, 2 raised to 3, 2 raised to 4. Sorry, 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. 16 is 2 raised to 4. 1 year. Rest of the bits can be 0. Will give me 0001, and since it's a 8-bit number, I'll pad the other MSB bits with 0. 00010000. Let's take one more, couple more examples. Let's take 99 in decimal. 99 decimal, equivalent binary for that. And also equivalent hex for that, hexadecimal for that.
So binary will be so if we start from the list LSB, so it will be 1100, then 0110.
Yeah, tell me from the MSB side, it will be what? 0110.
Yeah, from the MSB it will be 0110,
Mm-hmm.
then 0011.
That's binary. And what will be the hexadecimal equivalent?
So hexadecimal, this 0110 is 6, and 0011 is 3, so 63.
Okay. Any other answer?
No, the same answer.
Right. So it will be 63 in hexadecimal, or in binary format it will be 01100011. Okay, so you guys have a hang of it. So those are number systems you will be required very frequently to. Normally in Verilog design you will be working with binary numbers, but this is a 8-bit number. Now imagine you have a 32-bit number. You will have a lots of zeros and ones. So in such cases you will work in hexadecimal format, where 8 digits will represent 32-bit binary number. So normally you will work with binary and hexadecimal. Rarely you will work with decimal. You will never work with octal anymore. Nobody uses octal anymore. Keywords in Verilog. As we have just noted a few minutes earlier, Verilog is a case sensitive language. And like any other language, Verilog language has a lot of keywords: module, end module, input, output, in out, reg, wire, integer, etc. etc. All of these are lowercase values. So, but that doesn't mean that, let's say I'm writing a module. Module in lowercase is a keyword, but the name of the module, now if you write the name of the module in uppercase, all capitals, it will not be, there will be no complaint from the simulator, from the compiler rather. But you should not call module a module. You should name a module something more specific to what we're trying to implement. In this case, I forgot that. So module and mux 41 is my name of the module. So mux 41, because it's a 4:1 mux. So I can technically call it module. If I call it module in capital, it will be accepted because only lowercase module is a keyword. But calling module a module is doesn't make sense. So I will call it something that is relevant to my design. So any keywords in lowercase, all the keywords have to be lowercase. Anything that you use in lowercase has to be in lowercase throughout the design. Any signal names in uppercase has to be in uppercase throughout the design. We have already seen 0, 1, X and Z are the values that are available, that can be assigned to, or a signal can have one of these four values. 0 is logic 0, 1 is logic 1. X is unknown state. Typically happens when you have two drivers. This is called a multiply driven logic, and this will create a problem for you in synthesis. Any signal can only have one driver at a time. It cannot have two drivers. In this case, this signal here is getting a logic 1 from this side and a logic 0 from this side. So it doesn't understand what needs to be done at this point. So it generates X for you. You should never get X in your simulation. So if you are getting a X in your simulation, there is something wrong going on, and you should fix the problem there. Otherwise, the synthesis will not work for you because of this issue. Z is allowed, but it's a tri-state logic. It's normally used when you're using bidirectional ports. When you're using bidirectional ports, one of the direction has to be blocked. At a given time, only one direction works. So the other direction is blocked, and then the other direction is used, the first direction is blocked. Such cases, tri-state buffers can be used. Tri-state logic can be used. Assignments can be done in Verilog in this fashion. Now this is a continuous assign statement. Assign out is equal to not in. So the right hand side in will be inverted. This evaluation will happen, and then the out signal will be updated with this inverted value of input. Assign reg out is equal to reg in, left shift by shift time. So shift is some signal. Let's assume shift is equal to 2. So reg in value will be shifted left 2 times, and that shifted value will then go and get assigned to reg out. These are continuous assignments happening outside the always block. There are certain guidelines you should follow. Wherever possible, use combinational logic because they are very fast. Operands plus operators. So think about operators that you're using and make sure you're using it for the right operands. Assign out is equal to A and B to generate an AND gate for you. Assign EQ is equal to A equal to B. Single equal to is an assignment. Two equal to means it's a comparator. You're checking if A is equal to B. It's an equality operator. If A is equal to B, it will generate a logic 1 and EQ will be 1. If A is not equal to B, it will be logic 0 and EQ will become 0. Wire hash 10 INV is equal to not in. This we had seen in one of the earliest, very early slides. What we are doing here is there is a wire called INV. First, we'll wait for 10 time units. Hash 10 means it's a delay. Wait for 10 time units, then INV will be inversion of in value. So it's an inverter with a delay of 10 time units. Wire 7 down to 0C, this is a vector. C is 8-bit vector or 8-bit wire. And what is it getting? A plus B. So it's a 8-bit adder. A and B will be 8 bits in that case, and a C value will be updated with that one. Now, is this a full adder or a half adder?
I think it would be a half adder.
Why would that be?
C is supposed to. Well, I don't see the carry out sign. I mean, if we say C is the sum, then we need we need the carry.
That's why it's a half adder, right?
Yeah, for me.
Yeah, so that's the correct answer. We don't have a carry in. If we had this, let's just call it sum. This is single bit. Now this will become a full adder. A and B are inputs, 8 bits each. C in will be single bit input. If we add them, then you will get a full adder. And carry out will be another output that will be generated. So typically speaking, in that case, in such cases, we have to do like this. So we this will be 8-bit full adder. Or if we generated this, declare it this way. A plus B plus C in will generate two outputs, carry output and sum. This I can implement using a continuous assign statement, and this will give me a full adder. A and B will be 8 bits each. C in will be single bit. C out will be single bit. Sum will be 8 bits. That's how a 8-bit adder will be implemented. Since sum is 8 bits declared here. If it's single bit, then sum will also be A and B a single bit, sum will also be single bit in that case. So you have to keep in mind what are the operators used, what are the operands, and what kind of logic you are going to generate for that. Because synthesis will work this way. So you have to understand, if you remember, you have to understand how the synthesis tool thinks and would work. Based on that, you have to declare the logic, because this Verilog code will generate hardware for you after synthesis. Now in C language, this kind of loops are okay, or any other high level languages. Assign A is equal to B plus A. But in Verilog, in hardware design, we should avoid such kind of loops. Instead of A, you should have another variable called or signal called C. Then keep updating that and assign A equal to B plus C or something like that. So avoid this kind of logic loops. Wherever possible, avoid asynchronous design. So wherever possible, use clock as a reference signal. When you use clock as a reference signal, you design for sequential circuits. Sequential circuits using clock as a reference signal will give you synchronous design. About 90+% of the time, you would work on synchronous design. Only in rare case situations, you would work in asynchronous manner. Typically, uh, such situations will be interrupt driven, and even though they could be asynchronous signals, internally you will still use a clock, because the sampling has to work on a clock reference. Input of the signal could be asynchronous in nature, but internal logic will still end up being synchronous. So wherever possible, avoid asynchronous design and work on synchronous designs. Why synchronous design? If you remember, now synchronous designs work with respect to clock and clock edges specifically. So every positive edge of the clock or every negative edge of the clock, your design is evaluated and the outputs are regenerated again. So uh, whatever your clock period could be, so every few some very minute amount of time, your design is your outputs are regenerated after the evaluation of design. It will make sure that your design is never stuck in a particular value or in a particular mode where it is not coming out of that. Very less chances of your design getting stuck. So hardware not getting stuck means there is a very less chance that your product is in a is hung somewhere in a hung state, your laptop or a smartphone or anything for that matter. And in such cases, all you can do is reset and reboot your device or restart your device. But wherever possible in hardware design, use synchronous logic, which will avoid getting into that condition. Any questions?
No.
Okay. The next concept is very important called blocking assignment and non-blocking assignment. Blocking assignment is denoted this way: reg A equal to reg B plus reg C. The same thing by is denoted as a non-blocking assignment when we say reg A angle equal to. Now this is angle equal to reg B plus reg C. This angle equal to is for non-blocking, non just equal to will be for blocking. So what is the concept of blocking and non-blocking? Typically this is used for flip-flops, sequential circuits where clock is involved. Let's look at this piece of code. Always at passage clock begin reg A blocking equal to data, reg B blocking equal to reg A. End. What happens in such cases is it will start this always block on passage of clock. Data will go to reg A. Blocking means this statement will not go forward till reg A is updated with the data value. So immediate. It will wait till this that is done. Then it will go to the next statement and reg B gets reg A. What is reg A? Data. Data is already gone to reg A. So reg data through reg A will go to reg B. This is also blocking. So reg B, it will stop here till reg B is updated. So at the end of the always block, reg B will be equal to data value. If you convert this to a hardware design, data is going to reg A and reg B in single clock cycle. That's how blocking will work. Non-blocking assignments. Always at passage clock begin. So this will also work at every passage of clock. Reg C non-blocking equal to data. So that, what this means is the reg C is scheduled to be updated with the data value. And when is that scheduled? At the always end of the always block. When this block ends. Then it will not wait here. It will then schedule that and go forward. What is the next statement? Reg D is scheduled to be updated with the reg C value when this always block end. But what is the reg C value at that time? It's the old reg C value. It's not the updated value at that time, because the updated value will come to reg C when the end of this always block, because there is some minute delay, which is called a delta delay. And then it will go to the non-blocking means we will not wait here. Go to the next statement and reg D is scheduled to be updated with reg C value at the end of the always block. So data will go to reg C on the end of first clock cycle, and then that data reg C value will go and get updated with reg D on the second clock cycle. If you convert this to a hardware design, data is coming to flip-flop number 1. This clock is going to both flip-flops. On the first clock edge, first clock cycle end, reg C gets updated. Then it goes to reg D flip-flop, and reg D gets the same data value on the second clock cycle. Now, why do we need something? And I will tell you that we will end up using non-blocking assignments for our design purpose. So can you tell me, think about it, and why we need non-blocking assignments for design purpose, where this delay is involved? Did you get the difference
Can you
between
repeat the
blocking
question
and
again?
did you get the difference between blocking and non-blocking?
Yes.
Yes.
So now I'm telling you that we will be using non-blocking for design purpose, not the blocking one, but we will be using non-blocking assignments everywhere. Why is that? For that,
I think it's important because if we are to have if we have to have like data propagating from one point to another
Mhm.
with the synchronization of a clock, then it is important to have that small delay for the propagation within the circuit. But if we don't, if we use the blocking, then we are kind of restricting, the propagation of data from one to another. But if we use the clock, then I think they are in sync.
You're on the right path, but I would like a little bit better explanation. So I'll give you a hint. Now, the basic unit used here, since this is a synchronous logic, the basic block used here is a flip-flop, right? In blocking as well as non-blocking. So the basic component used is a flip-flop. So what are the timing delays involved in flip-flop?
Yeah, so I think you told us there is it two times like the was it time before it there was two times, so one I think was the propagation delay time and the time, and also the time it takes for the signal to stabilize so that it
So,
is
so one is called setup time,
recorded.
the other is called hold time.
Yes.
So what setup time and what?
So sorry.
So what is setup time and what is hold time?
Yeah, so I think setup time, I just haven't gone back to my notes again, but I think setup time is the time required for a signal to be in a like before the data is said to be a one or zero. It needs to be there for a certain amount of time. So I think that would be the setup time. Then the hold time. Oh, I think I forgot that, but
Okay, so I'll
what
explain
was
it.
it?
So since we are working with pos edge of clock, so edge of the clock, in this case, positive going edge of the clock. Now the data has to arrive and be stable for some time before the clock edge. That is called setup time. So the data has to arrive and be stable for setup time period before the clock edge. And after the clock edge comes, the data has to stay stable for some time after the clock edge comes. That is the whole time. The data has to hold on to that value. That's the whole time of the
Okay,
flip
okay.
flop. Now those are two times. But what is there some other timing delay involved for flip flops?
Yes, the propagation delay to move from one
Right.
state to another.
So what is that typically called? Do you remember the technical term for it? Technically, you're correct, but what would be the right term or the exact term for it, if you can remember? Let's wait for a minute. If you can recall.
Is it clock to Q time?
Yes. So it will be clock to Q delay, right? That is the propagation delay for a flip flop. So anytime a clock comes on the edge of that particular clock, the data will be assigned to Q. But there is some delay in between. That's called a clock to Q delay. So that clock to Q delay will happen in the flip flop no matter what, because flip flop is a hardware component. So now why are you using Verilog as a language? You want to design hardware. So if in real hardware, in real life hardware, this delay is going to be present, that delay has to be modeled in Verilog as a hardware description language. If I use blocking assignments, then that delay is not being modeled here. I'm bypassing that delay, or I'm short. short circuiting that delay. But if I use non-blocking assignments, I make sure that that delay which will happen in hardware is represented properly in my Verilog code, even at simulation level. Because if I simulate this non-blocking assignment, I will get a delay of one clock cycle on reg D. Reg C data will go to reg C on clock number 1. Then this value will go to reg D on clock number 2. This will happen in simulation, which is what will happen in real life design. So I have to make sure that I use non-blocking assignment for my design and simulation purpose. What is simulation? You are just going to simulate the design before you go and implement it on a FPGA or ASIC device. So simulation has to stay true. It has to show you the correct value, what will happen in real hardware. It may be correct or wrong, whatever it is, but whatever is going to happen in hardware has to be shown in the same manner in simulation. So I can do that with a non-blocking assignment. That's why I will end up using non-blocking assignments for my in my Verilog code, which will be the same code used for simulation and backend implementation phase. Do you understand this? Do you have any questions on the blocking and non-blocking aspects?
Yes, so it means that for a combination circuit that does not require any clocking, then blocking assignment will be good.
Yes, you're correct. This is for sequential circuits where flip-flops are considered. For combinational circuits, there is no clock required. In such cases, blocking assignments are okay. But one of the rules that we will see later on, I think there is the slide will come later on sometime. That is one of the guidelines and rules in Verilog is that, let's say you have, can I modify this? Yeah, I can modify this. So let's say you have this always block. Now this, or let's say I'm going to hand out this. So this is non-blocking. So let's say there is an AND gate and I'm assigning it I1 and I2. Technically speaking, a AND gate design, a AND gate is a combinational circuit. So I can technically use blocking assignment here because for AND gate design there is no clock involved. But the problem is the rule, as per the Verilog rule, you cannot mix blocking and non-blocking assignment in the same always block. You have to use blocking everywhere or non-blocking everywhere. So in that case, I end up using non-blocking even for combinational purpose. Okay.
It's
Or,
okay.
or wherever possible, one more option for me is if it's a very small design, I will have a separate always block. I will have a separate always block for my combinational circuit and I will have a separate always block for my sequential circuit. I can do that. But this may not be always possible. For smaller designs, I can do this. For bigger designs, I have to end up using this AND out in the same always block as the sequential logic. In such cases, I can use blocking everywhere or non-blocking everywhere. I cannot use blocking for sequential logic. We saw the reason for that. So I have to end up using non-blocking for my combinational circuit also, which will work okay. It's not an issue, even though this thing. So because since there is no flip-flop, the gate output there will be no delay in the gate output. It will work on the passage of clock and get updated immediately, even though we are including in the same always block. But this is another method where you can create a separate always block for your combinational circuit. Okay, so that's the solution in case you want that. Any questions?
Yes, maybe a last question is So we were talking about when you instantiate or we call it instantiate, like when you kind of write a new. Of course, now you are writing a module and you're putting an AND gate in it, right?
Mm-hmm.
So I don't know if we can go to one slide like that so that I can explain better.
Yeah, what's your question? There is an AND gate. So what is the question related to the AND gate?
Yeah, so no, it's not maybe a question, but just maybe curious because I was reading somewhere and they say whenever you're doing the gate assignments,
Mm-hmm.
that you should start with the output first as a convention. That the output should be the one that is declared first, then the inputs follow.
Oh, okay, yeah. So yeah, see, that's a guideline. Let me take a module example that we have seen. Yeah, in this case, we took input first and output was declared first, but then we declared input and then output. It doesn't matter. That's a guideline where whatever you have read is a guideline where some designers will follow that the outputs are declared first and then the inputs. But that's not a requirement. That's not a language requirement. I can declare inputs first and then outputs. Doesn't matter. So let's do
Not there.
this one, right?
Not
This is what we're
Yeah.
doing.
So like where you have XOR, you see where you instantiate component instances, right?
Okay, yeah. Okay.
So yeah, that's what I'm talking about.
See here also I'm okay. Here I have done the output first, but I can do the input first also. Just to prove my point, I will do input first here. And I'll tell you why that is allowed. So why I'm okay with doing this is I'll tell you because I'm using this method, formal and actual. I'm not using the shortcut method that we saw earlier, right? The formal dot A, dot B, and dot Y is the name of the ports of the XOR module. Y is
Okay.
output, A and B are inputs. Dot A is a capital A which is mapped to the local A input here. So I'm making sure that the A input of XOR2 is connected to A input of this module. Dot B bracket small b means the capital B, which is the input of second input of XOR gate, is mapped or connected to the small b input of this module. I'm making sure this is happening. Formal and actual, formal and actual, formal and actual. Dot Y, which is the output of this XOR2 gate, is connected to N1 wire here, this one. So I'm making sure using this formal and actual mapping that the output and input of this XOR gate are connected to the right ports or the local wires here, the local level. Now, if I do this, then I will be wrong. Why? Because XOR2, what is declared first is output. Now A, because now I am not doing the formal and actual technique, I am using a shortcut method. Only the actuals, local level signals. Small a will get connected to output Y. Small b will get connected to input A. And N1 will get connected to input B. Then I will be wrong. In that case, I have to, if I'm using a shortcut method, then I have to do it the right order. N1, comma A, comma B. So N1, local wire N1 will get connected
Okay.
to output Y of XOR2 gate. A of local A in small a will get connected to capital A of XOR2, which is first input. Small b, local level small b input will get connected to capital B of XOR2 gate. Because I am using this shortcut method, if I use this method, which is the right way of doing things, formal and actual, whether A input comes first or output comes first doesn't matter for the port mapping. You got it?
Yeah, I got it. So just as you said, so as long as you use the formal way, then as long as you map to the correct one, it doesn't matter which one. Even if you put B first, then as long as you use the formal and you connect the right one, then it's okay.
Exactly. Doesn't matter which order you are declaring it here. And whether when you are working with a very small design like this, small examples, this you will have very few inputs and outputs. Now imagine now here also with three inputs, two inputs and one output, I had to remember which was declared first in the XOR2 module. Imagine that you are working on very big designs which will have hundreds of inputs and outputs. How will I design? How will I remember this? Which is declared first in the module and which is declared second. That's why I will use this method. So I will ensure that the correct signals at the local level are mapped to the correct signals at the module which is instantiated using this method,
No,
formula match.
okay, okay, makes sense.
And typically what happens is this is very common that this module is designed by somebody else sitting in some other country and you are designing this module. So they will send you just input output ports and basic what needs to be done with it. So you have to take that and do the rest of the logic yourself. So it is very difficult to remember which order it was declared, etc. So use this method, formal and actual method. You will never go wrong in that case.
I got it. I got it.
Okay, so let me take this out. Okay, so I think we'll stop here today and then we will restart from Monday. It's Friday, so have a good weekend and then we'll talk again on Monday. Okay.
Yes, just before you go, so just to tell you, to remind you that, so by Monday, for us, it will be the normal time, but for you now, you'll come in 1 hour early. Yeah, because the daytime, what do we call it? The time changes on Sunday night.
Yeah, daylight savings is starting Sunday night, is it?
Yes,
So it will be one
actually
hour
Saturday night,
Saturday
tomorrow
night.
night.
So it will be 1 hour early for me or 1 hour late for you. Will start 1 hour early, right?
Yeah, for you it's 1 hour early. For us, it's just the same time. As long as I come in at 9 a.m. our local time, then it's just okay. But for you, because your time is not changing,
Right.
then you have to come 1 hour early. Yeah.
Right. I will remind the guys, support team guys who are scheduling the call. So and I'll also mark my calendar according. So I'm logging it at the right time in that case. Okay, thanks for reminding me. And I will make sure I'm logging in at the right time and we'll meet again on Monday in that.